Dear students, in the last class, we have studied about the periodic properties, that is, effective nuclear charge and shielding effects. They are the basic properties to deal with the periodic properties. So today, let us study about the periodic properties in detail. There are four important periodic properties. One is atomic and ionic radii. Second, ionization enthalpy. Third, electron gain enthalpy. And fourth, electronegativity. Coming to the first one, atomic and ionic radii. Atomic and ionic radii are the two important the radius of the atom and the ion. These two, along with there are many other the radius we come across. So these things we learn one by one. Atomic radius, it basically contains metallic radius, where the two metal atoms are bonded together by the metallic bond. We have covalent radius, we have van der Waals radius, and also we have ionic radius. In general, atomic radius is used in case of metal atoms, which are assumed to be closely packed spheres in the metallic crystals. So it is also called metallic radius. Atomic radius is half the distance between the nuclei of two adjacent atoms in metallic crystals. If I take an atom A and another atom B in the metal, these two are so closely packed with each other, half the distance between these two becomes atomic radius. So if A is the atom and B is the another atom, the distance between the nucleus of these two, that is AB, divided by 2. This AB distance can be determined through X-ray studies, but the absolute value of atomic radius cannot be determined. The distance between the two sodium atoms in a crystal of sodium is 372 picometer. So 1 picometer is equal to 10 raised to minus 12 meters. Therefore, atomic radius of sodium is 372 divided by 2, that is 186 picometer. The atomic radius can also be defined as the distance between the nucleus and the valence electrons. The atomic radius cannot be accurately determined because according to wave mechanics, an atom does not have a precise boundary surface. Coming to the molecules having a covalent bond. In such cases, we use the word covalent radius. Covalent radius is half the distance between the nuclei of two covalently bonded atoms of the same element in a molecule. Here, covalent radius is AB upon 2. Here, the two atoms A and B, they come to the maximum extent that much close, but it is not to the extent of the metals. Therefore, generally the covalent radius is slightly greater than the metallic radius. The internuclear distance in covalent radius is measured by X-ray diffraction or spectroscopic studies. For example, the distance between the nuclei of two hydrogen atoms in a hydrogen molecule is 74 picometer. Therefore, covalent radius of hydrogen atom is 74 upon 2 will be 37 picometer. The another problem, the internuclear distance between carbon and hydrogen in methane molecule is found to be 114 picometer. The covalent radius of hydrogen is 37 picometer. What would be the covalent radius of carbon? In such cases, covalent radius of carbon is 114 minus 37, that's equal to 77 picometer. Coming to the third type of atomic radius, that is van der Waals radius. This van der Waals force of attraction is generally found in noble gases. So because the noble gases, atoms are not in the form of molecules, they are in the form of the single atoms. And also we come across such van der Waals forces even in molecules which are in the form of gases. Van der Waals radius is once again much greater than the covalent radius, which is greater than ionic radius or the atomic radius. Van der Waals force is the attractive force between the two atoms which holds them together without the bond formation. Van der Waals radius is half the distance between the nuclei of two adjacent identical atoms of neighboring molecules. If I consider a molecule, that is A2 molecule and the B2 molecule, van der Waals radius is AB upon 2. In other words, it is the distance between the two non-bonded atoms of two adjacent molecules held together by van der Waals force of attraction. For example, van der Waals radius in hydrogen molecule is 120 picometer. This means nuclei of two adjacent atoms of the neighboring hydrogen molecule cannot approach nearer than 2 into 120, that is equal to 240 picometer from each other without bond formation. Similarly, two chlorine atoms cannot approach each other nearer than 360 picometer without bond formation. Therefore, van der Waals radius of chlorine is 360 divided by 2 will be 180 picometer. In noble gas atoms, only van der Waals force are observed. From the above, it is concluded that van der Waals radius is greater than covalent radius, which in turn greater than atomic radius. Coming to the ionic radius. Ionic radius is the distance between the nucleus of an ion and a point up to which the nucleus has influence on its electron cloud. The inter-ionic distance can be determined by X-ray measurements. Knowing the radius of one of the ion, radius of the other can be calculated. Example, the inter-ionic distance in sodium chloride crystal is 276 picometer. The radius of chloride ion is 181 picometer. Hence, the radius of sodium ion is 276 minus 181, that is equal to 95 picometer. Such problems will be asked in the examination. It is also seen that ionic radius of cation is always smaller than the corresponding atom. This is because cation is formed by the removal of electron or electrons, which shrinks the electron cloud due to increase in effective nuclear charge. Ionic radius of an ion is always larger than the corresponding atom. This is because anion is formed by the gain of electron or electrons, which expands the electron cloud due to decrease in effective nuclear charge. When we move from left to right in a period of the periodic table, atomic and ionic radii decreases. This is due to the addition of new electrons into the same shell, which results an increase in the effective nuclear charge. As a result, electron cloud shrinks and causes to decrease the atomic and ionic radii. When we move from top to bottom in a group of the periodic table, atomic and ionic radii increases. This is due to the addition of new electrons into the different shells, which results to decrease in the effective nuclear charge. As a result, electron cloud expands and causes to increase the atomic and ionic radii. Now let us study the variation of ionic radii in isoelectronic ions. The isoelectronic ions means the ions having the same number of electrons. Example, the nitride ion, oxide ion, fluoride ion, sodium ion, magnesium ion. All these ions, they contain the 10 electrons, but the number of protons in these are different. Nitrogen is having only 7 protons, magnesium is having 12 protons. So, increase in the number of protons increases the nuclear charge. As a result, electrons are held more strongly by the nucleus, hence ionic radii decreases from nitride ion to magnesium ion. Coming to the another aspect, that is ionization enthalpy. Ionization enthalpy is the minimum energy to be supplied to remove an electron from an isolated gaseous atom to form unipositive gaseous ion. You have to take an atom in gaseous state. When we supply, that also should be in the isolated form. When energy is supplied to this atom, then the isolated gaseous atom takes energy and the one of the electron in the atom gets ejected. The quantity of energy that is required to remove an electron is called ionization enthalpy. It is measured in kilojoules per mole or electron volts per mole. It is a direct measure of the ease with which an atom can lose electron. For example, if I take 1 mole of sodium in the form of gas, and when I supply the energy equal to 495 kilojoules, then all 1 mole of sodium turns into the sodium ion gas and 1 mole of electrons are ejected. The quantity of energy, that is 495 kilojoules, is known as ionization enthalpy. Smaller the ionization enthalpy, easier is the loss of electron. Ionization enthalpy could be referred as first, second and third ionization enthalpies or energies. If 1, 2 and 3 electrons respectively are removed from the atom, like the metal atom in gaseous state turns into the cation, that is first ionization energy. So in the second ionization energy, the metal ion in gaseous state, that is unipositive metal ion in gaseous state, turns into the bipositive metal ion in gaseous state. It becomes second ionization energy. Dipositive metal ion in gaseous state turns into the tripositive metal ion in gaseous state by eliminating an electron. So this becomes third ionization energy. So as more amount of energy is needed to remove an electron from the positive ion due to the decrease in atomic size and increase in effective nuclear charge, the second ionization energy is always greater than the first ionization energy, and the third ionization energy is always greater than the second ionization energy. Ionization enthalpy concerns with metals. This is because metal atoms have a tendency to lose electron or electrons. Ionization energy or enthalpy increases when we move from left to right in a period of the periodic table. This is due to the decrease in atomic size, which in turn increases the attractive force between the nucleus and outer electron. Ionization energy decreases when we move from top to bottom in a group of the periodic table. This is due to increase in atomic size, which in turn decreases the attractive force between the nucleus and outer electrons. Alkali metals have lowest ionization enthalpy, and noble gases have highest ionization enthalpy in their respective periods. Coming to the factors affecting ionization enthalpy. The first one, effective nuclear charge. Greater the magnitude of effective nuclear charge, higher is the amount of energy needed to remove the outermost shell electron. Hence, ionization enthalpy increases with increase in effective nuclear charge. So if I take the elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, their effective nuclear charges are 1.3, 1.95, 2.6, 3.25, 3.55, 4.55, 5.20 and 5.85. This shows that effective nuclear charge is increasing from lithium to neon. As it is increasing, ionization energy also increases from lithium to neon. So their values, for lithium it is 520.3 kilojoules per mole, for beryllium it is 899.5 kilojoules per mole, for boron 800, for carbon 1086, for nitrogen 1402, for oxygen 1314, and for fluorine 1681, and for neon it is 2080.7 kilojoules per mole. In this case, the beryllium and the nitrogen, they have abnormal increase of the ionization enthalpy. It is due to the completely filled and half filled subshells, which are more stable. In such cases, more energy is required. Coming to the second one, that is the size of the atom, that is atomic radius. Higher the atomic size of the atom, larger will be its ionization enthalpy. Higher the atomic size of the atom, lower will be its ionization enthalpy. For example, when I take hydrogen, lithium, sodium, potassium, rubidium and cesium, their atomic radius are 0.32, 1.23, 1.54, 2.03, 2.16 and 2.35. These are all in angstroms. The ionization enthalpy of these things are, for hydrogen it is 1312, for lithium 520, for sodium 495.8, for potassium it is 418.9, for rubidium it is 403.4, and for cesium it is 375.7 kilojoules per mole. This shows when we go down in a group, ionization enthalpy decreases. That's what it is given. When we move from top to bottom in a group of the periodic table, atomic radius increases due to the addition of valence electrons into the new shells. As a result, ionization enthalpy decreases when we move from left to right in a period of the periodic table. Atomic radius decreases due to the addition of valence electrons into the same shell. As a result, ionization enthalpy increases. So the example is given: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Their atomic radius are 1.54, 1.36, 1.18, 1.11, 1.06, 1.02, 0.99 and 0.98 angstroms. If I consider their ionization enthalpies in kilojoules per mole are 495.8, 737.7, 577.6, 786.5, 1011.8, 999.6, 1251.1, 1520.5 kilojoules per mole. Once again here, magnesium and phosphorus, they have abnormal increase of ionization enthalpy. It is due to the, once again, the extra stability rule, that is half filled and completely filled subshells. Inert gases have highest ionization enthalpy. This ionization enthalpy also depends upon the principal quantum number. Increase in principal quantum number increases the number of shells, which in turn increases the atomic radius. As a result, ionization enthalpy decreases. Another factor is the shielding effect. The magnitude of shielding effect is based on shielding constant, that is sigma. Greater the value of shielding constant, greater will be the atomic size, which in turn decreases ionization enthalpy. Lastly, the half-filled and completely filled orbitals. Elements with half-filled and completely filled orbitals are most stable than others. In such cases, more energy is needed to remove an electron. Hence, ionization enthalpy is high in such cases. Ionization enthalpy of beryllium, magnesium, nitrogen and phosphorus are much higher than the others in the same period. Noble gases have highest ionization enthalpy because of octet structure. Now these are the slides. It shows the atomic radius. In atomic radius, all are atomic radius, that is metallic radius, covalent radius, then van der Waals radius. Okay, they are all atomic radius. So how this is shown here? In case of the metallic radius, the atoms are very close to each other and half of the distance between the nuclei of two adjacent atoms is the atomic radius, that is metallic radius. In case of covalent radius, the two atoms, between the two atoms we have covalent bond, then the half the radius of this, half the distance of the two nucleus is covalent radius. Ionic radius of an element is related to the distance between the nuclei of neighboring cations and anions. Ionic radius of oxide is 1.40 angstrom. Then what is the ionic radius of magnesium ion if the distance between the magnesium and oxygen is 1.40 angstrom? Here also have shown the atomic radius. So it is the half the distance between the nuclei in covalently bonded diatomic molecules. atomic radius decreases across a period. It is due to increase in effective nuclear charge and decrease in shielding effect. And atomic radius increases down the group due to increase in the number of shells in the atom. So this is the ionic radius. So this is, we have shown the cation is smaller in size and anion is the bigger in size. And the ionic radius of an element is the the elements share the distance between the neighboring ions in an ionic solid. Cations are smaller than their parent atom, anions are larger than their parent atoms. So here also it is shown. If you take the sodium atom, its atomic radius is 154 picometer. But when you consider the sodium ion, so its ionic radius is 116 picometer. Similarly for magnesium, it is 130 picometer. Magnesium ion is 86 picometer. Similarly, if you consider the fluorine atom, its atomic radius is 71 picometer. But whereas the fluoride ion, it takes the electron and electron cloud expands. So therefore, ionic radius of fluoride ion is 119 picometer. Similarly, for chlorine atom, atomic radius is 99 picometer, whereas the chloride ion is 167 picometer. So this is also the slide shows about the ionic radii. Yes, this slide shows when we move from left to right in a period, that is from S block to P block. So the atomic radius, it decreases. Lithium is having 152 picometer, whereas the neon is having 70 picometer. And when we move down in a group from lithium to cesium, atomic radius, it increases. The lithium is having 152 picometer, sodium 186, potassium 227, rubidium 246 and cesium 265 picometers. So this table clearly shows about the atomic radius of the various atoms and how they vary across the period and along the group. So this is the another slide which also clearly explains about the variation of atomic radii across the period and along the group in S and P block. Coming to what is ionization energy or ionization enthalpy, both are same. So it is the amount of energy required to remove the most loosely bonded electron from an isolated gaseous atom to form a unipositive gaseous ion. This is known as ionization enthalpy or ionization energy of that atom. So this ionization energy, it increases when we move from left to right in a period of the periodic table, and it decreases when we move from top to bottom in a group of the periodic table. So this is what the slide it shows, how the ionization energy it varies, and also have explained about the cause for this. Students, go through these two, the periodic properties, that is atomic radius and ionic radius and ionization enthalpy, and also the various factors that affects the ionization enthalpy. Thank you.